You know, a broken shoulder, it sounds pretty straightforward, doesn't it? But what if I told you that fixing this one specific part, the very top of your arm bone, is actually one of the biggest engineering puzzles in modern surgery? We're going to dive into the hidden mechanics of this challenge and the incredible tech designed to piece it all back together. So, why all the fuss? Well, it really just comes down to this one number. This specific break, a proximal humerus fracture, is the third most common fracture in the entire human body. It happens all the time, especially as we get older. All right, so here's our game plan. First, we're going to get a handle on the challenge itself. Then, we'll open up the surgeon's toolkit and check out the hardware. After that, we'll get into the real fight for stability, where every millimeter counts, look at some brand new innovations, and finally, face the tough question of what happens when the fix, well, fails. So let's jump right into the core of the problem. See, this isn't just about a bone that's snapped in two. We're talking about a structural failure in a system that's often already weak. And that's what makes this so tricky. Let's get our eyes on the hardware. These are the main players. In image B, that's your workhorse, a locking plate. It basically braces the bone from the outside. Image C shows an intramedullary nail. Think of it like an internal splint that goes right down the middle of the bone. And D is a really cool hybrid of the two. These are the high-tech tools of the trade. So what is the fundamental problem we keep talking about? It's one word: osteoporosis. The bone itself just becomes weak, almost porous. And that changes everything. The surgeon's job goes from being like a master carpenter to something way harder. It's like trying to bolt a steel frame onto a crumbling brick wall. And that brings us to the toolkit. These are not just simple pieces of metal, not by a long shot. They are really sophisticated, constantly evolving devices, all designed to solve that one core problem. How do you fix a fracture when the foundation itself is unstable? And right here, this is a huge leap in the engineering. See, older plates just used friction. You'd press the plate against the bone and screw it in tight. But in weak bone, that pressure could actually do more harm than good. The real game changer was the locking plate. With these, the screws don't just go into the bone. They actually thread into the plate itself. It creates this single, rigid scaffold. It's less like a clamp and more like an internal support beam. And even in the world of locking plates, it's not a one-size-fits-all deal. There are all these different philosophies. You've got the fill plate, which is kind of the gold standard, the most tested one out there. But then you have fancier options like the NCB plate. It uses what are called polyaxial screws, which means the surgeon can actually change the angle of the screw for a more custom fit. Some designs are even ditching metal and using a polymer called PEEK for a fix that's strong but just a little more flexible. Okay, but having the best tools is only half the story. Now we get to the real battleground, the fight for stability. This is a game of millimeters, where the tiniest decisions can literally make or break the entire surgery. And in this fight, there are three huge debates that surgeons and engineers are always grappling with. First, positioning. Where exactly do you put the plate? Second, medial support. How do you reinforce that inner part of the bone to stop it from collapsing? And third, augmentation. Should you actually add something like bone cement to make everything stronger? So let's zoom in on that first one, plate placement. I mean, come on, a few millimeters higher or lower, does it really make that big of a difference? The answer? Oh yeah, it absolutely does. This computer simulation shows us exactly why. Using some seriously powerful software, researchers can visualize all the invisible forces. And look at this. When they shift the plate just 4 millimeters down, that's less than 1/4 of an inch, you see those bright red hotspots just explode around the screws. That is stress. That is the bone screaming for help. And if that picture wasn't clear enough, here are the cold, hard numbers. That bar on the right, that's the 4 millimeter downward shift. Just look at how much the bone strain skyrockets. That kind of strain is exactly what leads to failure, where the screws can literally just cut right through the soft bone like a knife through butter. The researchers who did this study summed it up perfectly. They said even a small distal malpositioning may reduce fixation stability, whilst proximal shifting of the plate may be beneficial. In other words, the margin for error here is razor thin. Okay, so if placing the plate is that finicky, what about that other big debate, augmentation? If the bone itself is the weak link, can we just make it stronger?
This is where surgeons sometimes use things like bone cement to give the screws a much better grip.
And the evidence for doing this is, well, it's just incredible. A huge analysis that pulled together tons of studies found that adding bone cement can reduce the risk of the implant failing by a whopping 81%. It makes a massive, massive difference.
So we get the challenge, we've seen the current toolkit, but of course, engineers are always pushing forward. So let's take a look at the next generation of tools designed to tackle this old problem.
I want you to meet the IEAAF. That stands for Intra and Extramedullary Assembly Fixation. It's a really clever hybrid design. It actually combines that internal support nail with an external plate, basically trying to get the best of both worlds for maximum stability.
And when they tested it in the lab, the data really speaks for itself. Stiffness is what we're looking for here. It's the key measure of stability. And look, the IF construct is just dramatically stiffer, way more stable than either a plate or a nail by itself. This could be a really big deal.
But